So with the earlier knowledge that we discussed in the previous class about the line charge distribution, the volume charge distribution, surface charge distribution, that expression we are going to make to find what is electric field intensity due to a small segment in a uniformly charged line. Here we can see that a blue line, however, the charges are uniformly distributed. The length of the line segment is L, and there you can see that a small line segment delta L, and which is around L distance from one end of the line, and there is a point, the P, which is at a distance of x from the center of this line, and similarly delta L, which is a small segment, which is we are going to consider about this segment. So what is the electric field intensity at this point P due to the small line segment which is uniformly charged, which is at a distance around r from the point P, and it is making an angle theta with respect to this line and the uniformly charged line. And here you can see that x is the distance from this point to the other end of the line, and L is the distance of the DL. This is the point we are considering, this line segment we are considering. This DL, the L is the distance of DL from one end of the line, and the alpha 1 and alpha 2 are the angle intercepted by this the end segment with respect to the line that is joining to the point P, and similarly alpha 2 is the angle intercepted by this segment at the extreme end of the uniformly charged line, which is making an angle with respect to the line which is connecting to the point P. So with all this information, we are going to find out what is the electric field intensity at point P due to the small segment DL. So later, with that information, we will find out what is the electric field intensity at P due to the entire uniformly charged line length. So earlier we have find out the electric field intensity is we can express in terms of line charge density, and here I just point out what is the infinitesimally small electric field intensity at point P. Let us represent it as dE. dE is the small electric field intensity due to the small segment dl, which is equal to line charge density into dl, which is upon 4 pi epsilon r square. So r is the distance made by the small segment from the point P. So rho L, we know that rho L is the delta Q, the delta 2 contained at this line charge segment, which is on the length of the segment. So delta Q become rho L dl. So this represent the charge at the point. Now if you resolve this vector, so electric field intensity is a vector at this point P. If you resolve this vector, the E is acting this way, delta E. So if you resolve this vector, we will get two components. One is the x-axis component and the another is the y-axis component. This is the angle theta. So this theta exactly match with this theta, because which is these two, this dotted line and this line charge density are parallel to each other. So this is theta. So this become dE. This is the dE y component and y-axis component, and this is dE x-axis component. So the electric field intensity at point P due to the dl we can resolve into two components, that is dEx and dEy. So dEx is, see, using the trigonometry we can see that dEx is dE sin theta and dEy is dE cos theta. So dEy is dE cos theta and dEx is dE sin theta. Now substitute the value of dE here. So dEx is dE the sin theta. So dE is rho L dl 4 pi epsilon r square sin theta. Now using some triangle we need to find the relationship of dl and r. This is to simplify this expression. So here we can see there is a triangle here. This is a triangle. I am taking out of this triangle. So here you can see the triangle. This is a small segment and this length is x minus L. Now if you take the cot theta equal to x minus L adjacent side by h. So x minus L become h cot theta. If I differentiate this function with respect to d theta, so this become minus dl by d theta, because when you differentiate x minus L with respect to x, this become minus dl, this become h. The differentiation of cot theta is cosec square theta, so minus cosec square theta. So dl become h cosec square theta d theta. Similarly, the sin theta here is equal to h by r. So r become h, which is on sin theta, that is h cosec theta. So now we can substitute the r and dl with this expression. So our dEx become rho L. So dl become h cosec square theta into d theta. So here the sin theta 4 pi epsilon. So r become h cosec square theta. So h square cosec square theta. So here h get cancelled, cosec square get cancelled. So finally it become rho L sin theta the d theta, and on the denominator side 4 pi epsilon h. Now I am going to integrate this function with respect to theta. So theta is changing from, if the a segment is on the one extreme of the line, so the theta become alpha 1. If the delta L is on the other extreme of the line, so that the theta become pi minus alpha 2. So Ex is the x-axis component of the electric field intensity at point P. Due to the total line is, I am integrating with respect to theta, because here we have the function d theta. So this is become alpha 1 to pi minus alpha 2 rho L sin theta d theta 4 pi epsilon h. This become rho L, you can take out, it is a constant, 4 pi epsilon h. So when I integrate the sine theta, it's become cos theta. So minus cos theta. So the upper limits and lower limits are alpha 1 and pi minus alpha 2. So if I substitute these limits, this become Royal 4 pi epsilon h cos alpha 1 plus cos alpha 2. So this is Ex component. Now we need to obtain what is the Ey component of the electric field intensity at the point P. Now let us figure out what is Ey component, that is delta E cos theta. So that become Royal dl 4 pi epsilon r square cos theta, and when you substitute the dl and r square, you finally come up with this way, Royal 4 pi epsilon and then cos theta. So I'm integrating from alpha 1 to the pi minus alpha 2. This is Ey. So this become Royal 4 pi epsilon. So integration of cos theta with respect to d theta become sin theta. So when you substitute the lower and upper limit, the expression become final sin alpha 1 sin alpha 2 minus sin alpha 1. Now if the line is infinitely long and this is exactly at the center, then alpha 1 and alpha 2 become same. The condition is if the line is infinitely long, then the point is exactly at the point P is exactly from the middle of the line, then alpha 1 become alpha 2. So if you use this information, and if you find Ex, you know that Ex is Royal 4 pi epsilon h. So cos alpha 1 plus cos alpha 2 become 2 cos alpha. So let us consider alpha 1 equal to alpha 2 equal to alpha. So Royal 4 pi epsilon h 2 cos alpha, and Ey become 0 because their sin alpha minus sin alpha become 0. So there is no Ey component exist, only Ex component exists. If the line become infinitely long, then alpha 1 minus alpha 2. That means if the line is extremely infinitely, then this angle become approximately 0. If you substitute alpha equal to 0 here, Ex component become Royal 4 pi epsilon h here 2, that so Ex component become Royal 2 epsilon h. This is Ex component, there is no Ey component, that means E is equal to Ex. So you can use this expression to find, there is a pi here, 2 pi epsilon h. So you can use this expression to find what is electric field intensity at the point P anywhere from a uniformly charged line. So that is Royal by 2 pi epsilon h. And interestingly, so we concluded that there is only Ex components exist, there is no Ey component because it becomes 0 when alpha is equal to 0.